Swayam Prabha. Digital India. Educated India.
Welcome to lecture 28 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Seemingly Unrelated Regression Models Introduction. Now, so far we have considered the estimation procedures and other inference procedures for a model of the form say y equal to x beta plus u. Now, sometimes you have a set of equations of this form. Just for example, suppose you consider the investment function for a firm and you represent the investment of a firm by some covariates, say you write a regression model of the form y equal to x beta plus u, y is the investment and x's are some covariates. Now, sometimes you have different firms and for each firm you have a separate investment function. So, you suppose you have 5 firms. So, for each firm you have a model of the form y equal to x beta plus u, a separate model of this form. So, what is the problem? You can estimate different models using the OLS procedure, but then there might be some relevant variables omitted from each of this set of equations. So, these set of equations may not be totally unrelated, means the disturbances of these equations may have some kind of correlation between them. Now, if you are applying the OLS procedure for estimating these equations separately, then you are not making use of the correlation between different sets of equations. Now, correlation means one set of equation has information about the other equations also. For example, if different firms are from IT sector, say all the 5 firms are from IT sector, then any changes in the policies of the government which supports the IT sector is going to affect all the 5 companies, all the 5 firms. So, you cannot say that all these equations are uncorrelated with each other, and since the 4 equations have information about the 5th equation also. So, while estimating the 5th equation, you can utilize that information, and if you utilize that information, then obviously it is going to improve your estimator. So, instead of estimating all the 5 equations separately, it may be worthwhile to estimate all the 5 equations simultaneously, and then it may lead to more efficient estimators. So, this kind of problem or these kind of models we handle in seemingly unrelated regression equations model. So, seemingly unrelated regression or SUR model is a multiple regression model, describes the behavior of a particular study variable using a set of explanatory variables. You have a multiple regression model which describes the behavior of a particular set of variable, you may denote it by y, and then you have a set of explanatory variables in x's. Then for explaining the whole economic system, the model may involve a set of multiple regression equations. So, instead of a single equation, you may have a set of multiple regression equations, and each equation explaining a particular economic phenomena. Say you have 5 firms, then for each firm you have one model. So, you have a set of 5 equations. Each particular equation explains the investment of a particular firm, but for explaining the whole economic system or for explaining the investments of all the 5 firms, you require all these equations, all the 5 equations. Then the question is, should different equations be treated separately for estimation purpose? Means whether you apply OLS procedure for estimating each equation separately, or you require some alternative estimation procedures. Now, all these equations may be seemingly unrelated with each other structurally. Means for each firm you have a separate equation. So, apparently it seems that all the equations are unrelated with each other, but these equations are linked through some statistical interaction among them. Say for example, as I mentioned earlier, suppose you have omitted some of the relevant variables from each of these equations, then it is going to affect the correlation between different disturbances. Means it may happen that if you omit some relevant variables from each of these equations, then different disturbances, terms corresponding to different firms, may be correlated with each other. So, there might be some kind of statistical interaction between different equations, and then the interaction is through the correlation between random error terms of different equations. So, in seemingly unrelated regression model, usually we consider this kind of interaction, the interaction through the correlation between random error terms of different equations, and such kind of correlation may be due to omission of some common factors from each of these equations, or maybe those firms are in the same sector of the economy. So, any changes are reflected in each and every equation. So, all the equations have some kind of correlation between them. Now, is it possible to improve the estimators based on individual equations by developing estimators based on the entire system of equations? So, one of the option is you apply say ordinary least square procedure separately to each of these individual equations. So, you get separate estimators for different equations, but then in that case you are not utilizing the correlation between random error terms of different equations. So, is it possible to improve these separate estimators, or is it possible to develop estimators based on the entire system of equations? Now, this is the objective of seemingly unrelated regression equations model. Then again the question is how to estimate the entire system of equations. If you want to develop some estimator which is based on entire system of equations, then how to get that estimator which is based on the entire system of equations. Now, we consider the difference between seemingly unrelated regression model and simultaneous equations model. In both seemingly unrelated regression model as well as in simultaneous equation model, you have a set of equations, but there is a difference between the nature or direction of dependence. So, this arrow actually denotes the nature or direction of dependence. Then in seemingly unrelated regression model, suppose you have two dependent variables or two separate equations and corresponding dependent variables are y 1 and y 2, and say y 1 depends upon x 1 and x 2. So, x 1 is going to influence y 1, x 2 is going to influence y 1. Then y 2 is influenced by x 2 and x 3. So, your model is of the form y 1 equal to say alpha plus beta 1 1 x 1 plus beta 1 2 x 2 plus u 1, and y 2 equal to alpha plus beta 2 2 x 2 plus beta 2 3 x 3 plus u 2. So, x 1 and x 2 are going to influence y 1 and x 2 and x 3 are going to influence y 2. And then in seemingly unrelated regression models, these errors might be correlated with each other. So, u 1 and u 2 are correlated. These are not independent of each other or uncorrelated with each other. So, this equation might have some information about this equation also, or this equation has some information about this equation also, and that information is reflected in the correlation between u 1 and u 2 or y 1 and y 2. In simultaneous equations model, the nature or direction of dependence is like this. Say suppose y 1 is influenced by x 1 and x 2. So, the model for y 1 is y 1 equal to alpha plus beta 1 1 x 1 plus beta 1 2 x 2 plus u 1. Then for y 2 is influenced by x 2 and x 3. Not only that, y 2 is also influenced by y 1. So, for y 2 the model is of the form y 2 equal to alpha plus beta 2 2 x 2 plus beta 2 3 x 3 plus gamma 2 1 y 1 say plus u 2. So, here not only x 2 and x 3, but y 1 is also involved. So, although in this equation y 1 is your dependent variable, but in this equation y 1 is behaving like an independent variable. But in this lecture we will discuss just seemingly unrelated regression models in this lecture and in the next lecture, and after that we will discuss the simultaneous equation model. So, in seemingly unrelated regression models, the jointness of equations is through the covariance matrix of the associated disturbances. Say in the previous example, the jointness of two equations is through the covariance matrix or the correlation between u 1 and u 2. Then the jointness provide additional information over and above the information available with the individual equations. You get information about y 1 from this equation, then since u 1 and u 2 are correlated with each other. So, you can say that the second equation also has some information about y 1. So, the jointness provide additional information over and above the information available with the individual equation. You have information contained in the equation, and then the second equation also has some information about the first equation. So, let us consider some examples of seemingly unrelated regression models, or some examples where one should apply seemingly unrelated regression models. So, in first example, your objective is to estimate demand relationships for a particular commodity for several households. Then price and income data are the exogenous variables. So, as exogenous variables, you have price of the commodity and income of the household. Then one may expect jointness of demand equations for different households through their error covariances. So, for different households, you have different models, different demand relationships. Apparently, those relationships are separate, but one expects jointness of demand equations for different households through their error covariances. So, the errors may be correlated with each other. Then in next example, while studying consumption pattern of a country with 20 states, each state has a consumption equation. So, for each state a consumption equation has been developed. So, in all you have 20 separate equations, 20 separate consumption equations. So, apparently those consumption equations look separate or different. Those consumptions equations are developed separately, but different equations may involve different variables and apparently look unrelated. On the other hand, consumption pattern of different states may have some kind of statistical interdependence. So, different states apparently those equations are separate, but any factor which is going to influence one particular state is also going to influence the other states also. So, this kind of correlation may exist between the error terms associated with the equations. So, you cannot say that those equations are totally unrelated with each other, unrelated in the sense that the equations, a particular equation does not have any information about the other equations. Those equations have some kind of statistical interdependence. So, the equation for a particular state has information about its consumption. Not only that, the consumption equations of other 19 states also have some kind of information about the consumption equation or consumption of that particular state. So, the equations are apparently or seemingly unrelated regressions, but not independent relationships. Now, we consider this example of capital asset pricing model or CAPM model. CAPM of finance evolves as a way to measure the systematic risk. Now, for the IH security, the equation is R I t minus R f t equal to alpha plus beta I R m t minus R f t plus U I t, say. Here R I t denotes the expected return of the IH security, and R f t is the risk free rate. So, R I t minus R f t will give you the expected return over the risk free rate. Then RMT is the expected return of the market, this one. RMT minus RFT is the equity market premium, means the expected return of the market over the risk free rate. Then beta is called the beta of the security, that particular security I. So, this is a measure of systematic risk of a security or portfolio compared to the market as a whole. So, this is the equity market premium, and then corresponding to the security I over the risk free rate, you have this much of return RIT minus RFT, and this beta I is a measure of systematic risk of a security, means this ith security, or it may be ith security or it may be a particular portfolio compared to the market as a whole. And then obviously, UIT is the disturbances. Now, CAPM describes the relationship between the systematic risk and the expected return of a particular security. So, this left hand side is the systematic risk and right hand side the expected return for the security I. Then risk free rate accounts for the time value of the money. So, this is actually the time value of the money. Then other components of CAPM formula account for the investor taking an additional risk. Again, beta is a measure of how much risk the investment will add to a portfolio that looks like the market. Means if in your portfolio you are adding the ith security, then how much risk you are adding. This is reflected in the value of beta. For instance, if a particular stock has beta greater than 1, then that particular stock is riskier than the market. And if a stock has beta less than 1, then it will reduce the risk of a portfolio. So, of course, on the basis of beta, one may decide whether adding that particular stock is going to increase his risk or it is going to decrease his risk. Then the information about the return of a security to exceed risk free rate by a given amount will provide the information about the excess return of some other securities. Now, in this model also, the disturbances are then obviously correlated across securities, because this information about the return of a security to exceed risk free rate by a given amount. This will also provide the information about the excess return of some other securities also. So, all these equations for different values of i's, different equations are not unrelated with each other or statistically unrelated with each other. Different equations not only have information about themselves, but they also have information about other securities also. So, disturbances are correlated across securities. Then estimating the securities jointly may provide better estimates than estimates based on individual equations. So, you have two options. You simply apply OLS to different securities and get the estimates of beta, but then you are not going to utilize this information, the information about a security contained in other equations. The other option is you estimate the securities jointly, then you may get better estimates, because you are utilizing more information for obtaining the estimators. Then next example is investment model. Now, we consider two IT companies, say Tata Consultancy Services TCS and Infosys. So, suppose N1 is a 25 cross 1 vector of observations on investment by TCS. You have 25 observations. V1 is 25 cross 1 vector of observations on stock market value of TCS, and K1 is 25 cross 1 vector of observations on year capital stock of TCS. So, you have observations on these three variables. Further, N2, V2 and K2, these are corresponding 25 cross 1 vectors of observations for Infosys. Then investment model for TCS is N1 equal to beta 1 1 L. L is a vector with all elements equal to 1. So, this is also a 25 cross 1 vector with all elements equal to 1, plus beta 1 2 V 1 plus beta 1 3 K 1 plus U 1, and the model for Infosys is N 2 equal to beta 2 1 L plus beta 2 2 V 2 plus beta 2 3 K 2 plus U 2. So, although the investment equations for two companies TCS and Infosys are using the same variables V and K, but their observations are different obviously. Again, in this particular example we have taken the same variables for both the equations, but it is not necessary. Both the companies may use different variables in their model as explanatory variable. Then we assume that expectation of U1 transpose is equal to sigma 1 1 I 25, expectation of U2 transpose is equal to sigma 2 2 I 25, just the assumptions of multiple linear regression model. Then as I told earlier, L is a 25 cross 1 vector with all elements equal to 1. Now, suppose we write y 1 equal to n 1, x 1 equal to L V 1 K 1. So, this x 1 is 25 cross 3 matrix, and y 2 is equal to n 2 and x 2 is equal to L V 2 x 2. So, again x 2 is also 25 cross 3 matrix. Beta 1 is equal to beta 1 1, beta 1 2, beta 1 3, beta 2 is equal to beta 2 1, beta 2 2, beta 2 3. Then we can write the model for TCS as y 1 equal to x 1 beta 1 plus u 1, and the model for Infosys as y 2 equal to x 2 beta 2 plus u 2. Then we apply OLS to two equations separately. So, in case we apply the OLS to two equations separately, we get the estimators of beta 1 and beta 2 as say B 1 equal to x 1 transpose x 1 inverse x 1 transpose y 1, and B 2 is equal to x 2 transpose x 2 inverse x 2 transpose y 2. So, obviously, if we consider these two equations separately, then B 1 is the best linear unbiased estimator of beta 1, B 2 is the best linear unbiased estimator of beta 2. So, there seems no problem. Both the companies are going to estimate their equations using the least square procedure, and they are getting the best linear unbiased estimators. Now, there is an issue. Two firms are working in the same branch of industry, both are IT companies. and investments or errors of two models may be correlated with each other. Say any changes in the policies of the government, and suppose those policies are going to support the IT companies, then those changes are going to affect both TCS and Infosys in a similar manner. Then these U1 and U2 may include some common factors. If any changes in say stock market is going to affect TCS, those changes are definitely going to affect Infosys also. So, although you have not incorporated those variables in the sets of explanatory variables, but those variables are going to affect both the companies. So, those variables are omitted variables, and then effect of those variables will be reflected in U1 and U2. So, you cannot say that U1 and U2 are uncorrelated with each other. There might be some correlation between U1 and U2. So, we take expectation of U1 U2 equal to say sigma 1 2 for all I and j, or you can write it as expectation of U1 U2 transpose equal to sigma 1 2 I 25. So, sigma 1 2 is the covariance between the ith component of U1 and say jth component of U2. The reason for such a correlation may be the state of economy whose effect is felt through U1 and U2 is likely to have similar effects on each of the firm. So, whatever changes are there in the state of economy, those changes which are felt through U1 and U2, because you have not incorporated those changes in your model. So, those changes are reflected through U1 and U2, and those changes are likely to have similar effects on each of the firm. So, this is the reason for such a correlation between U1 and U2. Now, the question is it possible to pool the two equations and estimate beta 1 and beta 2 more efficiently, taking into account the correlation between them? So, this is the question. So, instead of estimating the two equations separately, is it worthwhile to pool the two equations, or is it possible to pool the two equations? And then after pooling the two equations, we estimate beta 1 and beta 2 jointly and more efficiently, and that estimator after pooling the two equations takes care of the correlation between them also. Correlation between them means, now after pooling you expect that while estimating beta 1, you are also utilizing any information about the first equation, the model for the TCS, contained in equation 2 also. So, for the first equation you may have some information in the second equation also. So, after pooling you expect to utilize that information for estimating beta 1. Similarly, for estimating beta 2, you expect to utilize the information contained in equation 1 also, apart from the equation 2. So, this is the whole purpose of pooling these two equations and to estimate these beta 1 and beta 2 jointly. Now, we consider the general case of two equations seemingly unrelated model. So, we consider the following two equations seemingly unrelated model, say y 1 equal to x 1 beta 1 plus u 1, y 2 equal to x 2 beta 2 plus u 2. Here both y1 and y2 are n cross 1 vectors of observations on dependent variable. Then x1 is of order n cross k1 and x2 is of order n cross k2. So, these are the matrices of observations on explanatory variables in these two equations. So, notice that in the first equation you have k1 explanatory variables, whereas in the second equation you have k2 explanatory variables. There might be some of the variables common to both the equations, but it is not necessary that both the equations use same set of explanatory variables. Both the equations may use different sets of explanatory variables. So, k1 and k2 may be different. So, x1, x2 are matrices of observations on explanatory variables, and then u1 is n cross 1 vector of disturbances for the first equation, and u2 is the n cross 1 vector of disturbances for the second equation. Then we assume that expected value of u1 t is equal to 0, and this is equal to expected value of u2 t for all t equal to 1 to n. And then expectation of u1 t square is equal to sigma 1 1, expected value of u2 t square is equal to sigma 2 2 for all t equal to 1 to n. So, if you look at the two equations separately, then for both the equations the usual assumptions of multiple linear regression model are satisfied. For the first equation, expected value of u1 t square is equal to sigma 1 1 for all t. Similarly, for the second equation also. Then the expected value of u1 t u2 t is equal to sigma 1 2. So, the disturbances of two equations are correlated with each other, and the covariance between u1 t and u2 t is equal to sigma 1 2 for all t equal to 1 to n. Then in matrix notations we can write these conditions as, say, expected value of u1, which is a vector of order n cross 1 with elements u1 t is equal to 0. Expected value of u2 is also 0. Then expected value of u1 transpose, if you look at expected value of u1 transpose, this is equal to expected value of u1 1 square, expectation of u1 1, u1 2, so on, expectation of u1 1, u1 n, and so on, expected value of un 1, u1 n, and u1 1, and so on. Here you have expected value of un n square. Then expected value of u1 square is sigma 1 1, this is 0, then this is also 0. So, in the diagonal you have elements sigma 1 1, off diagonal elements are equal to 0. So, you write it as sigma 1 1 I n. Similarly, you write expected value of u2 transpose equal to sigma 2 2 I n, and expected value of u2 transpose is sigma 1 2 I n. Now, we combine these two equations, equation 1 and equation 2. So, we write y equal to y1 y2. So, this y is 2n cross 1 vector, and then we write x equal to x1 x2. So, you have 2n cross k1 plus k2 matrix. This x1 is of order n cross k1, x2 is of order n cross k2, and then you have 0 here of order n cross k2, and this 0 is of order n cross k1. Then again u is u1 u2, which is of order 2n cross 1. So, this is the vector of disturbances and beta is beta 1, beta 2. So, this is of order k 1 plus k 2 cross 1. So, this is the vector of regression coefficients. So, in fact, if you write this equation as say y 1 y 2 equal to x 1 0 0 x 2 and then we have beta 1 beta 2 plus u 1 u 2. Then you get the first equation from here, say y 1 equal to x 1 beta 1 plus 0 into beta 2 plus u 1. Then you get the second equation. Here we have y 2. So, y 2 equal to 0 into beta 1 plus x 2 beta 2 plus u 2. So, this is how we are combining the two equations here. Further, expected value of u transpose is equal to expected value of u 1 transpose, u 1 transpose, u 2 transpose, u 2 transpose. Now, expected value of u 1 transpose is equal to sigma 1 I n. Expected value of u 2 transpose is equal to sigma 1 2 I n. Expected value of u 1 transpose is sigma 2 1 I n and expected value of u 2 transpose is equal to sigma 2 2 I n. So, this is the variance covariance matrix of u. Now, in terms of canonical product, we may write this variance covariance matrix as, say, suppose you denote this matrix sigma 1 1, sigma 1 2, sigma 2 1, sigma 2 2 by capital sigma. Then in terms of canonical product, the variance covariance matrix of u is sigma canonical product I n and we write it equal to say V. So, sigma canonical product I n is the variance covariance matrix of u. Now, you can easily obtain the generalized least square estimator of beta. The GLS estimator of beta is, say, beta curl is equal to x transpose V inverse x whole inverse x transpose V inverse y. So, this is the GLS estimator of beta. We have simply applied the GLS procedure for estimating beta here. The variance covariance matrix of u is V. So, you get the estimator x transpose V inverse x transpose V inverse y. And then we substitute the value of V. V is equal to sigma canonical product I n. So, V inverse is equal to sigma canonical product I n inverse. Then sigma canonical product I n inverse is equal to sigma inverse canonical product I n inverse is equal to I n. So, we replace V inverse by sigma inverse canonical product I n. So, you get this estimator x transpose sigma inverse canonical product I n x inverse x transpose sigma inverse canonical product I n y. Then the variance covariance matrix of GLS estimator is, say, expected value of beta curl minus beta, beta curl minus beta transpose is equal to x transpose V inverse x whole inverse. Again we substitute the value of V inverse here. So, you get the variance covariance matrix of beta curl, the GLS estimator, as x transpose sigma inverse canonical product I n x whole inverse. So, this is the variance covariance matrix of the GLS estimator. Again this estimator is not feasible, because this variance covariance matrix sigma is usually unknown. So, one of the possibilities is that we estimate sigma and then we substitute that estimator here, means we replace this sigma by its estimator to get a feasible generalized least square estimator of beta. So, sigma is usually unknown. So, for estimating beta we proceed as follows. So, first we apply OLS to each equation in 2. So, we apply OLS to each equation separately and then we obtain the OLS residuals. So, for the first equation you get the residual E 1 equal to I n minus x 1 transpose x 1 inverse x 1 transpose y 1. So, this is the OLS residual for the first equation. Then the OLS residual for the second equation is E 2 equal to I n minus x 2 transpose x 2 inverse x 2 transpose y 2. So, you get this OLS residual for the second equation. Then for estimating sigma I, say suppose you have to estimate sigma 1 1, then we make use of this OLS residual. So, S 1 1 is equal to E 1 transpose E 1 divided by n minus k 1. Similarly, to estimate sigma 2 2, we use the estimator S 2 2 equal to E 2 transpose E 2 upon n minus k 2. Or in general, we estimate sigma I by S I equal to E I transpose E I upon n minus k I for I equal to 1 2. Then for estimating sigma 1 2, which is also equal to sigma 2 1, we use the estimator S 1 2, which is equal to E 1 transpose E 2 divided by, now you have different number of explanatory variables in two equations. In first equation you have k 1 variables, in second equation we have k 2 variables. So, we divide E 1 transpose E 2 by the geometric mean of n minus k 1 and n minus k 2. So, n minus k 1 to the power half, n minus k 2 to the power half, and this is equal to S 2 1 also. Or another option is that you divide by n minus maximum of k 1 k 2, and even if you take this estimator sigma head 1 2 equal to E 1 transpose E 2 upon n, this is also a consistent estimator of sigma 1 2. So, you can use any of these two estimators, and then we obtain sigma head inverse equal to S 1 1, S 1 2, S 2 1, S 2 2 inverse. Then it is equal to S superscript 1 1, S superscript 1 2, S superscript 2 1, S superscript 2 2. Then the feasible GLS estimator of beta is beta head equal to x transpose sigma head inverse canonical product I n x whole inverse x transpose sigma head inverse canonical product I n y. So, what you have done? You have simply replaced sigma by its estimator sigma head in the expression for GLS estimator to get this feasible GLS estimator of beta. Well, in the lecture on matrix algebra, we have discussed all these results for canonical product, but I am repeating all these results here also, because we are going to use these results in the next few lectures So, suppose A is M cross N matrix with ijth element A I j. So, A is equal to this matrix A I j, and B is P cross Q matrix with kth element B k l. Then we define A canonical product B as A 1 1 B, A 1 2 B, so on A 1 n B, A 2 1 B, A 2 2 B, so on A 2 n B, A m 1 B, A m 2 B, so on A m n B. So, what you have done? You take say 1th element of A and then you multiply it by the matrix B. So, you get a P cross Q matrix with elements A 1 1, B 1 1, A 1 1, B 1 2 and so on here. Again you get a P cross Q matrix here and so on P cross Q matrix here also. And in all you have n such matrices. So, A canonical product B has n q columns. Then how many rows are there? Say p rows are here, p rows here and so on. So, in all we have m into p rows. So, A canonical product B is of order m p into n q. So, this is the order of A canonical product B. Again I am just mentioning some of the results which we may require in the next lecture. Say suppose you have 4 matrices A, B, C, D, then A canonical product B into C canonical product D is equal to A C canonical product B D. Of course, the orders of A, B, C, D are such that the product A C and product B D is possible. So, this is how you can write the product of A canonical product B and C canonical product D. You simply take the product of A B, you take the product of B D and then you take the canonical product of A C and B D. Then the transpose of A canonical product B is equal to A transpose canonical product B transpose. And then from this first equation we observe that if A and B are square matrices, A is of order m cross m and B is of order p cross p. And not only square matrices, but they are non-singular also, so that you can define their inverse. Then A inverse canonical product B inverse into A canonical product B. Using this result, this is equal to A inverse A canonical product B inverse B. Then A inverse A is equal to identity matrix of order M, and B inverse B is identity matrix of order P. So, you get I M canonical product I P, and obviously, this is equal to I M P. So, identity matrix of order M P. And from here we observe that the inverse of A canonical product B is equal to A inverse canonical product B inverse. So, to explain many economic phenomena, instead of a single equation, often we require a set of equations. And then the question arises whether we should estimate those set of equations separately or we require some alternative estimation procedure. So, usually those equations look different in the sense that those equations are developed separately, but in many cases you may find some kind of correlation between them. Say, suppose you have demand equations for different countries, say for different developing countries, then those demand equations may have been developed separately, but any factors which are not incorporated in those models or in those equations may influence those equations in a similar manner, like any eventuality, like any war or the changes in trade policies of a particular group of countries may be going to affect all those equations jointly. So, there might be some sort of correlation between those equations. So, the question is, should we pool all those equations and estimate all those equations jointly? So, in this lecture we have discussed such kind of problems, estimation of such kind of equations called the seemingly unrelated regression models. We have observed that one can go for GLS estimation procedure for estimating those equations. So far we have considered just two equations model. In the next lecture we are going to generalize it for more than two equations model, when you have more than two equations in the set of equations. So, I am going to stop here. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.